Okay, let's talk about variables now. How we declare them, how we initialize them, and how we assign a value to them. So variables are memory storage locations. We want to give them meaningful names, so we'll use our identifier naming rules to give them meaningful names. And if we took an example here of a slope-intercept form of a line, if we wanted to write a program and implement this formula that y is equal to mx plus b, well, we can see that in this mathematical formula, y, m, x, and b are all symbolic variables. We could use these names, even though they're very short names, they'd be descriptive in our program. We could use those as variable names. When we declare a variable, we're going to give it a data type, and we're also going to identify the variable by name. Well, we say then, for declarations, that we have to declare a variable before we can use it. In order to declare a variable, we want to specify the data type and the name. So the general form is type and name. So down here below, if I wanted to create a variable in this example that says declare an integer variable named count. Well, here in this statement, I'm telling you that the name of the variable should be count. Now, an integer variable could be anything in the integer family. And it could be char, short, int, long. Typically, we'll just go ahead and use int here. So we made it of type int. So here's the data type, follows this form of type, and then the name of the variable is count. And then at the end of our declaration, we have a semicolon, because C programming statements end with a semicolon. And that's what this comment is here to remind you of. Well, that's declaring a variable, giving it a type and then a name. All right, and so here's some more examples with some meaningful names. So the data type here is int for integer, and employee num for employee number, ends with a semicolon. If I wanted to declare a variable named salary of type float, here's how we do it. A variable named letter grade of type char. Variable name checking account balance of type double, and a variable name of account number unsigned short. All right. Now, you can also declare multiple variables in one statement. So each one of these right here was a separate C statement. But if you want to declare multiple variables in one statement, then what we do is we first specify the data type here, float, and then here's three variables, temp Celsius, temp Fahrenheit, temp Kelvin. We go ahead and separate the names by a comma, right, to indicate we have a list. You can leave blank spaces, as many as you want, in between the names. You don't have to leave a blank space for the C compiler, but it makes it more human readable if we leave a blank space here. We end the statement with a semicolon. Right. Here, if you want to declare three variables named x, y, z of type int, here's how you can do it all on one line. Specify the data type first, then x followed by a comma. Comma is not part of the name, it just tells the C compiler, here's a list, and remember to end the statement with a semicolon. Right? So that's just a little bit less typing than putting everything on separate lines. All right, so where in a program are variables declared? Now, when we looked at Hello World, we said this was the general form of a C program, that we're normally going to have preprocessor directives at the top of our source code, global declarations, next, a section for that. Then we have our main function, and then if we have other functions in our program, we normally write them below. We write them separately. So far, all we've seen are preprocessor directives and main. So global declarations mean if we were to declare a variable outside of a function, that is a global declaration. We're going to try to avoid doing that for a while. It's not always a good practice. We'll learn later when it's good to do it and when it's not. For right now, we're working with the main function here. We can see then within here, inside the function is where we will declare variables. So where this is local declarations, local means these have been declared locally inside this function. So it has to be in between the set of curly braces that define the start and the end of a function. All right, so all our variables for right now we'll be declaring in main, and then we will write other programming statements to perform other actions. Scope. All right, scope refers to where can we use a variable. Right? So a scope is a region of a program. And if we were to declare variables outside here, global variables, global actually refers to the fact that we can access these variables anywhere within our source code from the time they were declared in here. So the scope has to do with where we can use them. We're not going to worry about global scope at this point. All we're going to do, as I said before, is we're going to declare all our variables for right now inside the main function. But we'll be able to use a variable after we declare it. We cannot use it if we don't declare it first, and I'll show you some examples of that later in this presentation. Right, so use a variable, you declare it, and then you go ahead and use it. So all that we'll be doing for right now is declaring everything within a function, main. Later, when we learn to write other functions, we'll learn that we can declare some variables in parameter list and within the function as well. The local variables, they're declared inside a function or a block of curly braces. So remember, we've learned that the left curly brace and right curly brace start and end our main function. Later, we'll learn that we can use blocks like this within a function to create local spaces. We'll use blocks like this to create compound statements later on. We don't need to worry about that right now, but what you do want to remember is that any variable that you create within here is local to this scope. So this represents scope, and that's why we use the word local, right? And you can only use those within this blocks of code. So for us right now, main, we'll declare something in here, be able to use it. So here's an example down below of main. Here, declared two variables, x and y. We say that these are local to the main function. They can be used within main. So anywhere after I declare it, I can use x and y in other programming statements. Here, notice this curly brace is the start of main. Well, here within main, here's another left curly brace. This can start a separate section of memory. And everything that you declare within here is local to the scope of this set of curly braces. So if I declare B and C in here, I could use them until I start executing code that's outside of this right curly brace. So this right curly brace ends this section here. These two go together, so the left and the right go together. And once I come down here, I've got a comment that say B and C are no longer in scope because they actually are popped out of memory after this right curly brace. Right, we'll see that later when we start writing more complex functions. Automatic memory allocation. Whenever you declare a variable, the operating system will actually take care of declaring and reserving memory for your variable. So it happens automatically. This is nothing we have to write anything specific to handle. It also deallocates. So when your program stops running, it deallocates the memory and indicates to other processes that that memory is available. Now, you can use the keyword auto. So another new keyword. By default, whenever you declare a variable, you have automatic storage. So if we were to just write int x, it's the same as declaring auto int x. That auto is automatically done for us. So rarely will you see the keyword auto written. You want to be aware that it's a keyword though, because you can't use it as an identifier name anywhere. Now, whenever we declare a variable like this int x, it's uninitialized. So uninitialized automatic variable has an undefined value until it's assigned a valid value of its type. Let's take a look at that in just a minute. All right, we'll see an example. All right, so talking about memory, it automatically allocates memory for us when our program's running, right? You've probably heard of RAM, random access memory. Your computer has different types of memory, but some of your program will be loaded into RAM when it's running, and there'll be space reserved for your program set of instructions as well as your data. Whenever you're declaring variables, it will automatically allocate memory for you, memory has an address associated with it, and at this address is where your information will be stored. So the amount of memory allocated depends on the data type and also on your hardware. Later we'll learn about microcontrollers, and we'll talk about the data type of the registers there. On a general purpose computer, if I'm using a 32-bit system, so remember C standard guaranteed, we have a minimum of 32 bits or 4 bytes of memory. So everything, memory is byte addressable. So here, these 4 memory addresses that I just randomly picked, 200, 201, 202, 203. Each one of these here could store up to 1 byte of information, and 1 byte is 8 bits. So here, if we declare the identifier, the variable count, that's its name, its data type is int, because an int requires 4 bytes of memory, the operating system would take care of reserving 4 bytes of memory for count. All right. Now, what is stored in there? We don't know because it's not initialized. When we declare this data type says how much memory to reserve, 4 bytes. Count basically is associated with the memory addresses that are created for us. But we don't know what's stored there. We have garbage stored there. So it's uninitialized, meaning we have not specifically told it what to store in it. You want to remember then that when we declare something like this and we don't initialize it, we don't know what's stored there. We usually say that it has garbage because we don't know what's stored in it. There's no number stored in it that's valid to our program, so we call it a garbage value. All right, let's then go ahead and perform an exercise so we can see this. So exercise 1, we want to try to determine the values of uninitialized variables. Right. So let's go back to our point slope form of our line equation. So we're going to assume that we're writing a program that will calculate some information about points on a line. And we're going to use the linear slope intercept formula. So here's just a reminder, if you don't remember the form, that the equation is y is equal to mx plus b, where m is the slope of the line, x and y are coordinate points on the line, b is the y-intercept, and that is where, when x is 0, this line crosses the y-axis. Right? So for our program, we're going to need to declare 4 variables, x, y, m, and b. Right? But what data type should we use for those? Well, in real numbers, we often have numbers to the right of the decimal point. We don't have integer numbers. So let's assume that we need some sort of floating point data. So let's see how we're going to create a C program and declare these variables. And I'm going to go ahead and start up code blocks and declare. And actually, we're going to write a program that looks like this. But what I'd like you to do right now is go ahead and start up code blocks or whatever IDE you are using. And I'm waiting for this to come up. All right, let's move this over here so we can see this. All right, so with code blocks, I'm going to create a brand new project for this. I want to put this in a project environment because I want to use some features of the debugger. I'm going to choose empty project. Click go. All right, project title. This is exercise 1, so I will just name this exercise 1. By default, it'll create the project on my desktop. If you want to save it somewhere else, you can click on this and you can browse to wherever location you want. Now remember, code blocks will go ahead and make a folder then by the same name as my project. All right, so I'm just going to say next here. I want to make sure I have this debug configuration. Both of these are checked by default, debug and release. I'm just going to go ahead and say finish. And now I have then a project. It doesn't have a file in it. And I want to go ahead and look here at my project tab. So I've got this workspace and I've got a project called exercise. I want to add a file to it. So file, new, here we go, file, new file. And then I want it to be a C source file. So I click here, say go. All right, so the first time this comes up after I've installed this, it tells me it's going to run the wizard. I'm going to go ahead and check this so it'll skip this page the next time. I don't want to see this every time this comes up. And then let's click on next. Remember, C, the code blocks will run both C and C++ code, so we want to make sure we check C here. We'll say next. File name with full path. All right, so I'm going to click on this, and I'm also going to name my file exercise 01, no spaces in there. Since we chose the C language by default, this will add a .c extension to it. And I want to make sure I have at least the debug version added to the project. I'm just going to click on all here out of habit, and I'm going to click on finish. All right, so notice now in our text editor, we have a file called exercise1.c. And here, if we click on this, we have a folder called sources, and here's exercise1.c, part of this program. Right, so what we want to do is we want to go ahead and declare 4 variables, y, mx, and b. And it's a good idea then of when we're working, so I've got this from a previous example here. It's a good idea to type in some comments. Let's practice our comments here. So I'm going to write a multi-line comment, so I'm going to say /*. Right. Now, I can fit, this starts a comment. I can actually then put more stars after this if I like. Notice by default, my code blocks leaves all my comments in gray. If I put a second star here, I get a blue character. All right, I'm going to say, what's the purpose of this program? All right, so I want some comments. So our purpose is to demonstrate that the values stored in uninitialized, so uninitialized, code blocks is trying to help me, but I don't want it to. Okay, now you don't have to put a star here. I just tend to put my comments in a block like this. Demonstrate that the values stored in uninitialized variables are unpredictable. All right, and I'm going to tab over, and I'm going to say, we say that uninitialized variables contain garbage values, right? And then to end my comment, I could have ended it on that line, chose to go down here, I need a */ end of comment. It's good to put these comments here so that later when you go back and look at this exercise, you know exactly what its purpose is. All right, now let's go ahead and create our main function. So int main, we can leave this blank, or we can put the word void here, your choice. Start of our function, and code blocks nicely fills in. So it started it with the left curly brace, code blocks filled in the right curly brace automatically. All right, so let's go ahead and declare our linear equation variables. So, and we just need 2 /. Everything to the right of this will be a comment. Declare linear equation variables. All right. So now to declare a variable, remember we need a data type. We said we thought these should be real numbers. Well, let's just use float. We could have used double. I just arbitrarily chose float. I don't think we'll have to be real precise or have really big numbers for a double. So here's my data type. I want a variable named x. Now I could put these all on the same line. I'm just going to go ahead and tab over and put a comment that says this is my x coordinate. Float y, semicolon to end the C statement. There's a comment that says there's my y coordinate. Float m, tab over, well, m is the slope. And you could have named that slope if you preferred to do that. I'm just sticking with the variables we have in our equation. And then b, Tabbing over is the intercept. Right? Now, I'm going to go ahead and hit Control S to save that. You can do File Save, or you can choose the Save icon. If you're having trouble, if your text is really small and you want to change the size of your text in your editor, you can go to Settings, Editor, wait for that to come up, and notice when it comes up there's a tab here, Editor Settings. Well, if I say Choose here under Font, I had set this at 14. It's regular, so I don't want any italic or any bold. You can choose the font type. I like the Courier type here. But if I needed to make this bigger, I could go ahead and say OK. Press OK here, come back. The text gets a little bit bigger. If you want to make it smaller, you can do that as well, just by changing the size. All right, let's go ahead now and let's type in Y. And I'm going to use spaces to make it more readable. So space, =, space M, asterisk, so that's the times X plus sign B, semicolon. Right, so we haven't learned any math symbols yet. We're going to learn that this is called the assignment operator. It's going to store information in Y. If I want to write a mathematical formula, I say M, my slope. The asterisk here is the times character. So this will do M times X, and then add the value, so the plus is addition in B, and we end our C statement in with a semicolon. Remember, we also need a return statement to return 0, right? We're at the end of main, so Control S. All right, so now let's go up to our build menu and just let's select compile, which is Control-Shift F9. Now let's take a look at what this did for me. I've got a lot of warnings turned on here, right? So I received warnings. Warnings, variable Y set but not used. Well, it's telling me that I'm going to store some information in here, but I'm not really doing anything else with it. The compiler tries to optimize for us. So it gives us warnings when we're doing things that are writing code that isn't used. We want our code to be as efficient as possible. Well, that's why the compiler is letting us know that we're doing something, but we're not really using anything. And we want to get rid of statements like that normally, but in this case, we're doing this to prove a point. So we're going to leave this in. Notice it also gave us a warning here. M is used uninitialized in this function. It's the same thing for X and B as well. And whenever you get a warning like this, this is telling you you have garbage in memory and you want to go back and get rid of these types of warnings. But in our case, we're trying to show then that the values stored in the initialized variables are unpredictable. But we want to see what's stored here. In order to do that, we don't know how to print out these values yet, but let's start using our debugger. I want you to place your cursor here to the left of this statement, where Y =, M times X plus B. And now I want you to go to the debug menu. And I'm going to go down and choose Run to Cursor. What that does is it goes ahead and starts building your program. It comes up and tells me my layout's changed. You can save it if you want. I'm just going to say no here. It will pop up. It popped up this on my other screen. It'll pop up the terminal window. We don't have any output specified. I'm just going to minimize that so it code blocks automatically starts that for us. Notice here there is a yellow triangle to the left. When I chose Run to Cursor, what this did is it ran all the code in my program up until this statement. So it went ahead then and declared X, Y, M, and B. Right. What I'd like to do though is see what's stored in here. So this watch window has popped up. In case you don't have a watch window, so I'm going to go ahead and close. If you have your watch window already, you can leave it open. In this case, I'm going to close it. In case you don't see one, go to your debug menu, go to debugging windows, and choose watches. And then it pops up your watch window. All right, so now when this popped it up, I've now got this screen showing here, locals. Locals are variables that I've declared that are local to the function I'm in. So I'm in main right here. And notice it's got some numbers associated with x, y, m, and b. These are just whatever numbers happen to be in that memory location where it loaded these variables. These are nothing that we've initialized. And now you should be doing this with your own computer, and you should not be seeing these same numbers. You should be seeing different numbers on your computer, right? If we were to go ahead then and execute this next line of code, so we could either go to the debug menu and choose next line, which is what we'll do here, or there's some icons here as well for next line. What that does is it executes the next line of code. And notice it used the values that were stored in m, x, and b and went ahead and assigned them to y. So see where y is in red here in this watch window? Well, that is the value that is now stored in y's memory. And usually the last variable that's changed in code block shows up in red like this. The others have gone to black now. So you can see, if you're running the debugger, what affected memory and what's currently in memory. Now, this is just all garbage values, right? Not meaningful at all. All right. And then when we want to end our debugging session, I'm just going to go ahead and choose this red X here, which will then stop the debugger. Same way you can go to the debug menu and choose stop debugger. Right. And that just stops the program from running. Remember, we're only able to use the debugger because when we created this project, we said we want the debug environment. So see right here, this build target for debug. When we build, we could go back and forth between debug and release. We're going to be working in debug all semester. All right. So I'm just going to go ahead and minimize this. And all right, so back here in this slide, right, when I ran this earlier, this code, these are the values that I got. When I ran everything through the debugger, you can see here in the watch window, I got these values here in memory, right, to show you what I got for that example. Now, what I'd like you to do is, I want you to follow, you should have been following these same steps. And then on Canvas, there's a discussion forum. Here's the name of the discussion forum. I want you to go ahead and post your values for X, Y, M, and B out on that discussion forum. So each student in the class should go to that discussion forum on Canvas and post your values. I want to do this as a point where we'll see that everybody should have a different set of values, because it's all depending on your computer and what happened to be in the memory of the computer you were using when you did this. So I just wanted to do this to make the point that we had the garbage values. I want you to all get the experience of using the debugger. The debugger will help you immensely throughout the course of this semester. All right, so make sure you do that before moving on with the rest of this. All right, let's talk about the assignment operator. So we had this statement back here. We had this y, this equal sign. The equal sign isn't equality in this case. It's called the assignment operator. And that's how we are able to store information or assign information to variables. So here's an example where I've declared a variable. Its name is x. Its data type is integer. Remember, when I first declare it, it has garbage in it. If I want to put a known value into it, I can go ahead here and say, here's the number 20, this constant. I want you to assign 20 to the memory location of the variable x. And that's what it does. The assignment operator takes everything on the right-hand side of the assignment statement, and it evaluates that to a numerical value. Let's go back here in our program here where we said m times x plus b. What this statement did is everything to the right of this assignment operator was evaluated. So it took the value stored in memory for m, took the value stored for x, multiplied m times x. We'll talk about order of operations when we learn about these arithmetic operators. But just like math, multiplication takes precedence over addition. So the multiplication took first. That produced a numerical result that was then added to what was stored in B. That then produced an expression, a numerical expression, which was assigned to the variable y. So that's what the assignment operator does. Everything to the right is evaluated to some numerical expression, and then it is stored to the value on the left. That's why we say here the value of the expression on the right-hand side, the 20. Well, 20 is just 20. There's no math that needs to be done, but this is a numerical value that is taken and assigned to the memory location named x, our variable named x. So it's assigned to the variable on the left of the assignment statement. We'll see later everything to the left of the assignment statement must be a variable name. And this is how we will initialize variables then. So back here, we declared x and then said go ahead and store 20 inside of x, or assign the value of 20 to x. We can also do it all in one line. So we can have our data type here, int, our variable name, and we can have the assignment operator and whatever value we want to assign to it. So here I'm declaring it, and I'm also initializing count to a known value of 0. We want to do that most of the time when we work with numbers. If we're going to use them in math, we have to have some sort of known value in there in order for the outcome of our program to make logical sense. So what happens then, if count happened to occupy these memory addresses, so remember 4 bytes, each one of these stores a byte, so each memory address on your computer is byte addressable, so stores 1 byte. So if we were to store zeros, remember everything that's stored in memory is stored in binary. Well, a 32-bit binary 0 looks like this, 32 individual bits, all 0. Here's some other examples then of declaring and initializing variables. So you can do multiple ones on the same line. Here in this example, the data type is float. There are 2 variables we're declaring. One is named fx, the other is named fy. We're storing the value 1.23 into fx and the value of 1.0 into fy, ending with a semicolon. The next line, the data type is integer. Variable name is x. We're going to store the value of 9 in x, store the value of 4 in y, and store the value of -2 in z. Right? End statement with a semicolon. All right, so each one of these variables have been initialized with a known value. In example 2, we're going to see that the variables fa and a are initialized to known values, but fb, t, and d contain garbage. So you want to be careful when you do this, because this is a little bit hard to read, and I wouldn't really recommend writing code that looks like this. I'd write things on separate lines to make them more readable. But you can write it like this. Just be aware of what's happening here. Data type float, the variable name is fa. We're going to assign the number 0.14 to fa. We're going to declare fb, but fb has garbage in it. Here our variable is of data type int. So t has garbage in it. We're not assigning anything to it. So comma separated list, point that out again. We're going to declare a. We're going to store 0 in a. And then comma to separate it from the next one, we're going to declare D, and D will have garbage in it. So F, A, and A both have initialized known values to our program, but FB, T, and D here have what we consider to be garbage values for our program. Okay, here's a concept then about memory. And when you're working with different devices, it is important to know how numbers are stored in memory. It's important to know that sometimes you're transferring information from one device to another. Sometimes you have to access a particular byte or a particular bit of memory. So in that case, you want to know how the number is stored in memory. We're talking about the term endian or endianness, and that refers to how bytes are ordered within computer memory. Remember, computer memory is just a sequence of bytes, and each byte has a number called its address that programs refer to. So back up in our table here, we just had this very short segment of memory that had 4 bytes in it. It had a memory address of 200, 201, 202, 203. So this is a byte address, byte address, byte address, byte address. There are 4 separate byte addresses, right? Each could store 1 byte or 8 bits. All right, so that's what we mean by each cell has a number called its address that programs use to refer to it. Little endian, increasing numeric significance with increasing memory addresses. We'll see an example on the next slide. Big endian, decreasing numeric significance with increasing memory addresses. The important thing is different instruction set architectures use different endianness. So if you're sending things from one architecture to another, then sending something from an ARM architecture to an Atmel microcontroller or an x86 architecture, it's important for me to know about endianness and how my bytes are being assembled. Here's an example then of big endian and little endian. We have a 32-bit hexadecimal number. Here's our hexadecimal number. Remember, then you need 4 bits for one hex number. So 1, 2, 3, 4, 5, 6, 7, 8. We have 8 hex numbers. 8 times 4 bits is 32 bits. All right, so this is our hex number, 987654EF. Just separated each one of these groups to make it easier to read. If we're storing this number using little endian, but remember this 9 is the most significant digit in here. This F is the least significant. We're reading from left to right. Least significant is F, most significant is 9. What little endian does is it stores the most significant byte. So our most significant byte here is 98. So it's going to store 98 at the largest address. Little endian stores the most significant byte at the largest address, and then it goes in order. So the 76 goes at the next address, the 54 at the next, the EF at the smallest address. Big endian is just the opposite. It's going to take the most significant byte, so the 98 most significant byte, and store it at the smallest address. And then the 76, the 54, the EF. Like I said, this is important to know when you're accessing data at the bit level. So eventually we'll learn how to work at the bit level, and we'll come back to these concepts at that time.